Hello and welcome back to Manifolds, the video series where we learn how to integrate on generalized surfaces. In fact, in today's part 38, we will start talking about the integration of differential forms. However, first, this is just an introduction because we will go into more details with the next videos. Here I first want to tell you why integration on manifolds and differential forms on manifolds are connected at all. But before we start with that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. Moreover, with the link in the description, you find additional material for all the videos, like PDF versions, quizzes and so on. And with that, I would say let's immediately start by recalling what we already know from integration. And there let's fix a one-dimensional function f. So it just goes from R to R. And we can already assume differentiability because later between manifolds we want smooth functions anyway. However, this property is not needed to have the one-dimensional integration. And for the integral we have a nice visualization if we consider the graph of the function f. One possibility is the Riemann integral approach, where we approximate this area below the x-axis and the graph of the function f by rectangles. Then the picture looks roughly like that, and by making the rectangles finer and finer, we will reach the whole area here in the limit process. In other words, what we get out is the integral of f. And the common notation we have for that is the integral symbol f of x dx. Now, in the case that you don't know anything about the Riemann integral, please watch my real analysis series where we discuss everything about that. However, now it turns out that there is also a more modern version of an integral, which is called the Lebesgue integral. And indeed, this is something you find in my measure theory series. Now, the visualization for the Lebesgue integral does not look so different from the Riemann integral. In fact, one usually also just takes rectangles. The big difference is just that one takes the y-axis as a reference point for the partition. This means that the two rectangles here are connected in this partition because they represent the same values on the y-axis. However, I don't want to go into the details here, you just need to know that there are two different theories to get an integral. And in fact, the Lebesgue approach is definitely the better one. It gets a more powerful theory out and more functions are integrable. But since for smooth functions the Riemann integral makes no problem at all, it's not so important which notion we take here. Both lead to the same number, the integral of the function f. Hence, if you are fine with the Riemann integral even in higher dimensions, then you can just take that for the following. And only if you already know the Lebesgue integral, you should see every integral here as a Lebesgue integral, simply because it's more general. Now, what I should also mention here is that obviously we only integrate over a bounded domain, a bounded interval here. And this is what we usually also put into the notation of the integral. For the Riemann integral we usually write a to b, and for the Lebesgue integral we put the whole domain as an index into the integral. Indeed, since the Lebesgue integral is so general, we need this notation in the general case. However, as I already said it, all these details are not so important. The important fact is that you already know what the integral of an ordinary function is. And now here we want to generalize that to manifolds. And there I have to say that the two-dimensional graph pictures here are not the best to see what actually happens here. It's better to interpret f of x as a density at the point x. Because then we still have our one-dimensional real number line and there's no confusion in which dimension we work. But then what we have are different densities at different points on the number line. And then instead of a graph, we could visualize the different values of f like this. And then the approximation from above as a rectangle would mean here that we just take a small line segment. So you could say we cut the line here, and this is what we call our delta x. And now we say we take the density in the middle, and this would be f of x. Hence what we get is f of x times delta x. So we have the one-dimensional density times the length. And there, if you think of mass density, what we get out is the total mass inside this interval. Hence, in order to get the whole mass of the whole line, we just have to sum up these small parts. And there you should see, if you do the splitting of the line with same-sized intervals, what we get is the same as the Riemann integral approach. But of course, the same argumentation holds for the Lebesgue integral as well. So roughly speaking, what we want to do here is to sum up the different mass parts, and then if we do it finer and finer, we get the correct value, which is the integral. The good thing is, if you do it like that, then the dx in the integral also makes sense. The sum goes to an integral symbol and delta x goes to dx. Okay, and then what we get here is that the integral is the total mass of the line. I think this whole approach here is a good visualization for the integral because it gives you the correct dimension. We have a one-dimensional integral and the picture should also be one-dimensional. You should not be confused by calculating areas. The only thing you have to adjust here is that densities could also have negative values, and usually we don't talk about mass, we just say we have the one-dimensional length again. So the length here is just weighted, stretched with the density. And now the good thing is that this whole picture also works in higher dimensions. So for example, we could have f from R2 into R. This means f is now a density on the plane. So similar to before, we can just use brightness levels to visualize the values of f. So we have a density in the area and our approximation could work with small rectangles in the plane. So not so different as before, now we have density times area. And what we get is an approximation of the mass inside this small section, and then we just have to sum up all again. And then again, in some limit process, you know we get the total mass, which is the integral. So now most importantly, this is a two-dimensional integral. And to emphasize that, let's use two real variables x and y. And then instead of dx, we can write dxy. And then again, in this two-dimensional case, we get the total mass as well. So again, we have a two-dimensional integral here, therefore a two-dimensional picture with two variables in two different directions. And there you should already see, this is how it should work for a two-dimensional manifold as well. However, for a manifold we don't have this flat picture here because a manifold is banded, curved in some way. And this is exactly what makes the only difference. The visualization with the densities is still correct. Therefore, as a first step, let's take R2 as a manifold now. This now means that we can take differential forms on R2. So please recall, a differential form omega is something that puts an alternating k-form to each point on the manifold. Hence, omega sends a point P in M to an alternating k-form, which is now given as f of P, which is our density at the given point, and times the 2 form we could call dx wedge dy. You know this is the standard 2 form in R2, and it's the same at every point P. More precisely here, we have an alternating 2 form on the tangent space TPM. However, since R2 is completely flat already, we know that the tangent space is just R2 again. Hence, the only thing that changes for the differential form if we go through the points P is the density in front. And you also already know that we call the whole thing differential form if the function in front is differentiable. So maybe as a quick recap, what happens if we put two vectors into the differential form? So we fix the point P and then we put V and W into the form. This means now we have to know what the wedge product does again. And indeed it's not so complicated. Here it just takes the first vector V for dx times the second vector in dy minus the opposite order. So not so complicated at all. However, now you should know that dx of a vector gives the first component of the vector. So we should say this is v1. And of course, dy gives the second component of the vector. And now if you see this whole combination here, You might recall that this combination of dx and dy gives us the determinant in R2. So what we actually have here is Fp times the determinant of v and w. And there you should see this is the volume form in R2, so the form that measures the area in R2. So it's the same as before, we have density times area to get the mass at the given point. Therefore, summing up everything will give us the integral. In other words, here it makes sense to write something like integral over m of omega, plain as that. So there are no d's involved, we just write a form and that's it. The reason for that is simply that the volume measure or the area measure here is already included in omega. Or if you want, you can just say in omega we already find dx and dy. Therefore, this whole thing is a more general interpretation of the integral symbol because it tells us that this dxy actually represents a differential form. Hence, in the case we work with manifolds, we should use this notation here on the left and not the one on the right. However, still the meaning is the same, it's just the two-dimensional integral as we have explained it before. But now the crucial insight here is that it changes for a manifold because a manifold is curved. Which means we need to take the tangent spaces at each point and we need to measure volumes inside each tangent space. And this measuring of the two-dimensional volumes here could change depending in which tangent space we work. Or saying it more precisely, in the differential form, not only the density depends on P, but also the differential form, the volume form afterwards. So the whole idea is still the same, but now it makes sense to define an integral for a differential form on a manifold. It just generalizes the integral we already know, and we can also use this integral for the definition if we go to local charts. However, how to do this correctly, we will discuss in the next video. So I really hope we meet again and have a nice day. Bye bye.